Is the mic on? It's on here. I guess they'll let me know if they can't hear me at the other end. So last time we were talking about the full set of nonlinear differential equations that describe the motion of the aircraft. And we talked about how we could integrate them numerically like is done in some of the flight simulation software. Today I'll show you a way to linearize the equations so that we can Laplace them. And the way you do that is you pick an equilibrium flight condition, like a cruise, and then you look at small changes or small perturbations on that equilibrium flight condition. So we'll only look at the dynamics about, say, a steady state flight of 200 knots going forward. And because we say that those changes are small, then we can neglect products of small numbers and get rid of the nonlinearity terms. Actually, we neglect them. So there's a process to doing that. I'm going to give you the exact, there's 4 steps to success in this, and I'll detail each one so that you can keep track of that, and then I want you to do that on the homework next week. Follow those and show me those 4 steps. So the first thing we do is we define a reference equilibrium flight condition. And it might be called a steady state because that's what equilibrium means. It means things are not changing. And we're going to do this in the stability axis that we talked about last time, which means all we'll have is forward velocity. Yeah. Oh, yes, I need to change my view, don't I? Thank you. Appreciate it. Thanks for watching the chat. We're going to do that in stability axis, which means we only have a forward speed. Because in the stability axis, we have no side slip and no vertical velocity because the axis is pointed into the wind. So all we have is forward speed in this initial steady state flight condition. So what we do is we say, we have a U0. This is the reference condition. And that's equal to the total velocity vector. So that's our airspeed. And we say V0 is 0, W0 is 0. We talked about that over there. There is no roll rate, no pitch rate, no yaw rate. So this is a true cruise condition. And it's typically what's used. It doesn't mean we can't pick a different one. We could say, okay, we're in a steady state turn or a steady state pull up, but we're just going to do this one. The heading angle, we'll just say we're going north. And we could be climbing or diving, so we're going to allow that. And there is no bank angle. Now later on, we might specialize it to just steady state level flight, but for now we're going to allow that. And then the forces and moments will define, okay, there's a steady state force in the XYZ direction. This would be the lift drag and probably no side force. And then we'll have a rolling moment, yawing or pitching moment, and yawing moment. There will probably all be 0 for this steady state flight condition. So this is our reference. And then we're going to look at small changes on top of that. And then those are the dynamics. We're going to look at the dynamics of the changes on top of that. So we have to go over here to the other board in a minute and say, added to each one of these is going to be some small change. So we caught up in here? Everybody good with that side? So that I know the Zoomers are probably good. Okay, so. And now we look at small changes or perturbations. And that's on top of the steady flight. So we're going to say, okay, our total forward velocity is the steady state part plus some change. And so this is going to be the small perturbation. The airplane may speed up 1 foot per second or slow down 1 foot per second, something like that. And that can change with time. So U0 is not a function of time, it's just 150 knots. This is a function of time. So U0 is a constant. Delta U is a function of time. And there's where we're going to get our dynamics. Okay, so then V, the total side velocity, starts out at 0, but we can have a change in that. Same thing with downward velocity, which would give us a change in angle of attack. For all the variables, we do this. We start out with the steady state part, and then we add on a small part. Some books, when they do this, will use capital letters for the steady state part and then lowercase for the perturbation part. Often when you're handwriting it, it's hard to tell, or maybe even in the book, typesetting it, it's hard to tell, especially with like angles, what's capital theta and what's small theta. So this book does what I think is really smart, is that they put the 0 on the steady state part to indicate that. What does bug me about the book is that if there is no steady state part, if this is 0, then they don't put the delta. I think they just got tired of doing deltas. It simplifies it. So in the text, there is no delta if there is no steady state part. So there's no delta here, here, here. But there is a delta on theta because there's a theta 0. And then there's steady state, possibly steady state parts to this, so there's deltas on that. So I'm going to follow the book's notation, but just be aware that and it actually doesn't present a problem because most of these are 0 to start out. But keep track of that when you're looking in the book, and when I'm going through the lecture, if there's no steady state part, there's no delta. So we'll just have a delta U and a delta theta, and that'll be it. So first we'll look at the force equations. And notice that I'm even mixing the lowercase and uppercase. I guess we're good over here, but so let's make sure we're consistent here. So that's P, Q, and R. Huh? Did I not do that? Yeah, we're good, aren't we? Yep. All right. Thanks for keeping tabs, though. All right. So the first thing we want to do is, what are the equilibrium conditions? I'm sorry, the equilibrium equations, which means no perturbations. And these are called the steady state equations. So that's the first thing we do, is we find the equilibrium equations. Now you won't need to do this in your homework because I'm going to give them to you here, but you will need them. All right, so if we look at these equations, and if there's no perturbation, that means we're just dealing with the first column in all of these. And this is going to be pretty simple because most of the stuff is zero in the steady state flight condition. So if we look at that, we have an x0, because we have an x0 over there. And we have a minus mg sine theta 0, because we have a theta 0 over there. And we have an m u0 dot, but u0 is just a number. It's like 100, so the derivative is 0. And all of the rest of this stuff is 0. Right? Because you look over there at the first column, all that stuff is 0. So the steady state force equation in the x direction is just this. If we do the y direction, we have a y0 sine of 0. Even though we have a cosine theta 0, we have the sine of no bank angle. So that's 0. And all of this stuff over here is 0 because there is no W0. And the derivative of that would be 0, and then P and V and Q and U. There's a U0 here, right? But Q is 0. Well, we get a 0 over here. Everybody follow? What am I doing wrong here? Oh, that's the Y0. Yeah, okay, so we're good. Now we need to do the Z. So this one's easy. And then Z, we just have a Z0. Again, looking at the first column. Here we got mg cosine theta 0. Cosine of 0 bank angle is equal to m times 0, because all of this stuff is 0. So these are called the steady state equations, and they have to hold because if there's no perturbation, we're in that steady state flight. And so they have to satisfy the equations of motion at that 0 flight condition. Because it's a valid flight condition, right? Okay, so you'll need these for your homework. And now I'm going to do the first two equations here in class, and you're doing this one for homework. So the process you're going to do is exactly what I'm going to show you right now. So you'll need this steady state equation here. I'm going to use these two, and then we substitute all of the stuff on the right-hand side into these equations, and then we follow the process. Everybody up to speed? We're good on how we're going to do this? Let me go back over here for a minute. There's a little work we can do ahead of time. Notice we have sines and cosines, and those are definitely nonlinear, so we need to linearize those with our small perturbations. So that's kind of a preliminary step, so you can call this step 0. So if we have the sine of an angle plus a small perturbation, that's a sum or a double angle formula. So we look that up on Google or in a book, or you just remember these. Right, so there's the double angle formula. And we say what's small? Well, what's small is delta theta. So can we do anything with that? So the cosine of a small angle is approximately 1. And the sine of a small angle, we could put 0, but we could just say it's the angle in radians, and that's all we really need to do to linearize. So we don't want to knock out anything more than we have to linearize the equation, so that works. And then when we have cosines, double angle formula for that. And again, what's small? Cosine is about 1, and the sine is the angle in radians. So we'll use that. And if you look over in the equations on the other board, there's sines and cosines of phi, like here. But that's not such a big deal because there is no phi 0. So we'll just have the angle itself in there, and it'll be small. Okay, so here's Dr. Steck's, and other people use these too, but I'm claiming it for today. 4 steps to success. Did I spell success right? Are there 2 C's? Yeah, it didn't look right. Doesn't that seem weird? There's 2 S's too, right? Okay, I'm glad you guys are better spellers than I am. All right, so obviously I don't have 4 steps to success in spelling. So here's step 1, is to substitute. We kind of did that up here. We substituted the small perturbation plus the steady state. So substituting into the x equation, let me flip back over to that real quick so we can look at it. So we're going to plug in x0 plus delta x. We're going to plug in theta 0 plus delta theta. We're going to plug in u0 plus delta u. And then we're going to plug in q and w and r and v because there are no v0s or r0s and so on. So that's what we're doing. So we're taking that list that I had on the board over here earlier, the list of steady state plus small perturbation. We just, every time there's a variable here, we substitute in. So we get and there's the work we did for the sine of theta 0 plus delta theta. So that's the thing up here. So that's step 1. And we'll go ahead and do the y equation too, because I promised you I'd do that one. Again, I just looked at my list. Where there was a u, I put u0 plus delta u because that was my list. Whereas a p, I put p, w. There was no v0 dot, so I don't have that here. And then the z equation is for homework. So that's u. You can do the same steps. Okay, that's step 1. Step 2 is to say, oh, u0 dot is 0 because it's steady state. Well, that was easy. But make sure you show me that step. I'm going to look for it. So u0 is, for example, 200 feet per second. So what's the derivative of 200? It's 0, right? Because it's just a number. It doesn't change with time. Okay, step 3 is to make small perturbation assumptions. In other words, we're going to neglect small stuff. You've heard the expression, don't sweat the small stuff, right? So we're going to look at this and we're going to knock out anything that's small that we can, but only enough to get it linear, which means we don't want stuff times other things that vary with time because we can't Laplace them. So we're not going to just go crazy and knock out everything that maybe can be small. We're going to just make as many small angle or small approximations. like we already did that when we were doing this, is we were making small approximations here. So what are we going to do here? Let's look at all the terms. Well, here's a delta x, but it's all by itself. It's linear already, so just keep that. This is sine of an angle. This is just a number. Here we got delta theta times a number. So we can keep that. It's linear. It's not multiplied by anything else. How about over here? We've already said that's gone. Here's delta u dot all by itself, so that's good. We know how to Laplace that. But here we got q times w, and both of these are time variables, so we can't Laplace that. All right, but that doesn't mean we can necessarily throw it away just because we don't like it. We have to have a good reason for it. So this is a product of small numbers. So can we do anything with that? So maybe we're talking about like 0.01 times 0.02. Notice we get 0.02, like an even smaller number, right? So that sounds like something we could knock out, especially since we can't Laplace it. And in fact, that's the whole point of this linearization, is we say, okay, these are small changes. So compared to just 0.01, this is 0.002, and so we can say, well, it's small. So we're going to neglect products, keyword products of small perturbations. If it's all by itself, no product, we keep it, because there's no justification. It's not two small numbers times each other. So how about this? You want to knock that out? R is a perturbation. Side velocity is a perturbation on top of the steady state flight. So yes, we can say this is small. So a key thing that I want you to get from this is we are not saying that this is zero. We're saying it's small and we can neglect it. And in fact, we are saying it's small compared to other numbers. Because if we had 1,000 plus 0.1, we could neglect the 0.1, right? But if we had 0.2 plus 0.1, we couldn't neglect either one. So we have to say this is small compared to the other stuff. So don't say Q times W is 0. That's not correct. It's just small. Okay, how about the next equation? Y0 is a steady state. There's the perturbation, but it's not multiplied by anything, so we got to keep it. Here we've got cosine of a number. Got to keep that. Here we've got delta theta. That's small, so let's see what we can do with that. Here's a number, and then sine of phi, we can approximate as that, right? The angle itself. And then we look at this and we go, okay, we got a small times a small. So let's neglect that. So anytime you have a product, you neglect. How about over here? We say this is small product. How about here? R times U0. Small times big. We've got to keep that. Small times small, we can neglect. Again, you're going, wow, there's a lot of stuff going on. Well, no, it's not. You just look at each term and you say, not small, not small, not small, small, but okay itself, small, but when we multiply it times this, we got to throw it away. So if you'd like it better, you can multiply this phi through both of these terms, and then it's real obvious you have a delta theta times a phi, and then you have that small product. So step one is to substitute. Step two is to knock out the steady state dot terms. Step three is to look through and see what small products you can get rid of. And then the last step's an easy one. we subtract, so this is step 4, subtract the steady state equation. Why? Because I see it here. I better use another color. So we'll call this the red step. Does that show up on the screen? Yeah, it looks okay, doesn't it? So if we look here, here's x0 and here's mg sine of theta 0. And that's all steady state stuff. There's no perturbations in there, no dynamics. And if we go over here to the other board, we see that those two numbers subtracted together are 0. So you can substitute in and make it 0, or you can just subtract this equation. Right, it amounts to the same thing. And then here, y0 is equal to 0, so we would subtract that from the y equation. So that's why we needed those steady state equations, is for this step. So here's the only steady state part here, because here we're going to have cosine, but that's going to be multiplied by phi. So what we're left with are our small perturbation equations, which are these here. So we subtract out that literally with an eraser, and we subtract out this term, and we're left with mg times that. So there's our steady state equation. So we have time, I've got 1 minute. I'm going to write those over here. Everybody good with that board over here? Are we still getting caught up? So here's what we end up with. And we're good. And you're going to do the Z one. Exact same process. All right, so next time we'll look at the moment equations, and I'm going to do the first 2 of those. You'll see the process happen again, and then you'll do the third one in the homework. I didn't save time. Let me give you your quizzes back real quick. I apologize. I meant to save an extra 5 minutes for that. So we can do this quickly. Colin Beal. Colin here. Sam Dennis. Jonathan Gutierrez. Sam Heim. Dylan Helms. Down to him. Shritha. Jenids Behringer. Is it Jennings or Janidis? I'll get, hopefully. Johnson, Noah. Stefan here? Okay. Tristan Kraus. Rayleigh, perfect timing. Theron Miller. Lucas, write your name a little bigger. Pasnak, Sid. Can you fly it down to him? You get that down that way, please. Singh, Deepak. Maddie Smith. Maddie Lee. Suzuki. Harun Suzuki. Van Beek. Van Meer Hagel. Ziegler.